Into what's called Hess's Law. So our learning goal for today is to be able to determine the enthalpy of any reaction essentially indirectly. So let's get into what Hess's Law is. So what Hess's Law states is that if you can add together two or more thermochemical equations in order to produce a final thermochemical equation, then you can do the exact same thing to their enthalpies in order to calculate the enthalpy of the final reaction. So basically, whatever you do to the reactions, you would do to the enthalpies, and you can actually calculate the enthalpies for certain reactions. Okay, so what this means is if you flip the reaction, aka reverse it, you will flip the enthalpy sign. If you happen to double the quantity of a reaction, you must double the enthalpy. We'll see exactly what I mean by this, but Hess's law will allow us to calculate the enthalpy for any reaction as long as we know the enthalpies of what other reactions have to take place in order for that one to happen. So some strategies to help out with Hess's law. One of the first most important points here is just work backwards. If you see where everything needs to be finished, then it'll give you a better idea of exactly how to manipulate the other reactions that you have. You essentially just want to make everything match up. Reverse the reactions when you need to, multiply them to ensure that the quantities are correct, and you really want to watch out for states of matter, just because you are looking to match that final exact reaction exactly the way that you see it. Okay, so let's do some examples because this can be a little confusing. So here we want to calculate the enthalpy for the final reaction of nitrogen and oxygen forming two nitrogen dioxides. Okay, and we are given these two reactions. Okay, N2 and O2 make 2NO, and the enthalpy for that. 2NO plus O2 creates 2NO2, and the enthalpy for that. So if we go back to our steps, we want to essentially work backwards. So let's see where we're at, where we want to be. Okay, so here's the reaction that we're trying to get to, and let's see how we can manipulate these things. Okay, so if we see, I like to start with the products. Okay, so if I have my 2NO2 gas on the product side, I'm just going to look at these reactions. Oh, look, it's already on the product side on the second one. So I don't have to flip anything here. I want a nitrogen on the reactant side. Here, in this reaction, I have a nitrogen on the reactant side. Now I want O2, and I want two of them on the reactant side as well. We'll have an O2 here and an O2 here. Considering that these reactions are going to be combined, okay, O2 and O2 would give me my 2O2. If you see we have a 2NO on the product side and on the reactant side, because they're the same thing on opposite sides, they essentially cancel each other out. And so if we just add together these reactions, we end up getting N2 plus O2 plus this O2, because we're adding both reactions, no other reactants, and it's going to form 2NO2. It's got a little lazy here, didn't write the states of matter, so I'm just going to do that real quick. Okay, and then if we just simplify this, we get N2 gas plus 2O2 gas makes 2NO2. This is exactly the reaction that we wanted. Now, in order to get this reaction, all we did was just add together these two reactions. So that means to get the enthalpy of this reaction, it is just the sum of the other two. So it's going to be 180 plus negative 112, which equals to 68 kilojoules. So in this example, we really didn't even have to do anything. All we ended up doing was just summing up the two reactions. So this just kind of gives you the really basic example of what Hess's law is about. We combine two reactions to get this final one, so we just combine the two enthalpies together. Let's look at a more challenging example. We want to calculate the standard enthalpy of formation for carbon disulfide liquid given, these three other reactions. So like I mentioned, let's take a look and try to get to where we want to finish. Okay, so the reaction for the standard enthalpy of formation for this is going to be carbon solid plus 2 sulfurs solid, and that's going to produce carbon disulfide liquid. Okay, so this is where we want to get to at the end. So again, I like to start with the product side. So carbon disulfide is a product here. I'm going to look at these three reactions. I see carbon disulfide right over here. But oh wait, it's a reactant. Okay, so in order to get that into a product, I have to flip this reaction. So I'm going to take CO2 gas plus 2SO2 gas. Okay, and we're going to make carbon disulfide liquid and 3 oxygens gas. Now, because I flipped the reaction, my delta H flips as well. So it was negative 1072. Now it's going to be positive 1072. Okay, so I took care of that. I have my carbon disulfide as a product now. So let's focus on the reactants. Here, I need carbon to be a reactant. If I take a look at these reactions, oh look, carbon's right here, it's a reactant. I don't have to touch this reaction as of right now. Okay, so this carbon's fine. Now I need 2 sulfurs as a reactant. If I take a look here, I have a sulfur as a reactant. Great. The problem is there's just 1. I need to get 2, and I don't see any other way to get 2. So I must double this entire reaction. So I'm going to get 2 sulfur plus 2 oxygens, okay, produces 2 sulfur dioxides. Now, because I doubled the reaction, my enthalpy gets doubled as well. Okay, so I end up getting negative 296.1, and I'm just going to put a times 2 over here. That way we can see that it became times 2. Okay, so I have everything exactly where I need to be. Let me just write this final reaction here so we can see now how we're going to combine everything. Okay, so if we just start eliminating things. So when we're going to combine all of these, let's see what's left over. So I have a 2SO2 on the reactant side and a 2SO2 gas on the product side. These are going to be canceled. Okay, I have a 3O2 over here. I have a 2O2 plus an O2, which makes 3O2. So these are all gone. I have a CO2 over here, and I have a CO2 over here. You can see all I have left now is carbon solid plus 2 sulfur solid. It leads to carbon disulfide liquid. The delta H here remains the negative 383.5. So the delta H of this reaction becomes the sum of all of these. So 1072 plus negative 291.2 times 2 plus, I'm just going to squeeze that down here, negative 383.5. And we get a total of 86.3 kilojoules. So our final enthalpy for this reaction is 86.3 kilojoules. So you can see here how we had to manipulate some of the reactions. We flipped one, we doubled the other one. Whatever we do to a reaction, we must do to the enthalpies, but this helps us figure out the enthalpy for any reaction.